Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are exploring marketplace interference bias, which is a challenge that arises when actions taken for one user affect outcomes for others in interconnected systems. This episode is based on a tech blog titled Using Marketplace Marginal Values to Address Interference Bias, written by the Lyft data science team. You can find the blog link in this episode's description. Throughout this episode, we will dive into both the business motivation and the technical approaches. Now, let's dive in. Lyft is a major player in the ride-sharing industry. It operates in over 600 cities across the United States and Canada. The platform facilitates millions of rides each week and supports a vast two-sided marketplace for riders and drivers. At this scale, Lyft is constantly running A/B testing experiments to test new features, pricing strategies, and operational changes. Most of those experiments are randomized on the user side, either on the riders or drivers, with the goal of measuring the impact of a treatment on engagement, earnings, or the general marketplace efficiency. But here is the catch. Lyft is a tightly coupled ecosystem. Changes on one side of the marketplace, say offering discounts to riders, don't just affect those receiving the treatment. They can ripple out and influence the experience of other participants, including those not in the treatment group. Take a simple example. If a discount increases ride demand, it might stretch driver supply chain, leading to longer wait time or reduced earnings elsewhere in the system. Standard A/B testing assumes that each user's outcome is independent, a condition known as the stable unit treatment value assumption. But in a multiple-sided platforms like Lyft, that assumption breaks down, and this phenomenon is known as interference bias. Interference bias is more than just a statistical nuance. It can distort results and lead product teams down to the wrong path. Without accounting for it properly, a test might suggest that a rider promotion is highly effective, but in fact, it is simply redistributing supply or cannibalizing engagement elsewhere. To address this problem, Lyft's data scientist team need a new approach, one that could scale with the platform and reflect the complex interactions between riders and drivers. Now that we understand the business problem, let's shift gear and dive into the technical side to see how the team tackled this interference bias. The blog first outlines several standard strategies where companies use to reduce interference in experiments, this including cluster randomization, time split experiments, region split experiments. Those approaches are all trying to minimize the inter-cluster interactions by either creating dedicated clusters or using time or geo-region to naturally make the split. While these approaches are helpful in mitigating those interference bias, these methods come also with trade-offs. Usually, it comes with some reduced statistical power, a longer experiment durations, and less detailed insights. To overcome those limitations, the data scientist team developed a more flexible and scalable framework called Marketplace Marginal Values, or MMV in short. The core idea here is to quantify the true marginal value that each driver and rider contributes to the marketplace. In a marketplace like Lyft, where resources are limited and supply-demand dynamics are tightly linked. MMV help reveal how impactful a change on one side of the marketplace truly is. Put simply, MMV estimates the change in total gain, whether that's completed trips, revenue, or other business metrics. The gains result from adding or removing a single rider or single driver. In operational research, this is known as the shadow price. By using MMV, Lyft ensures that experimental results reflect not just direct effects, but also the system-wide consequences of an intervention. Here is how the MMV-based approach works. First, the team formulates an optimization problem that captures the dispatch process within a well-defined matching cycle. This involves generating a dispatch graph representing the current state of matches between riders and drivers. Solving this graph enables the team to compute incremental values, which is how much gain would be added or lost by introducing or removing a participant. The next step, the team determines how frequently to solve this optimization problem. At Lyft, this is done every 1 hour in a megacycle. During each cycle, MMVs are estimated for all eligible riders and drivers, offering a real-time view of each user's marginal contribution to the marketplace during that period of time. Once these values are calculated, they are stored in a centralized table. From there, the team uses them to compute MMV-corrected metrics, which are incorporated directly into experiment analysis. These metrics are further refined using standard techniques like Cupid to reduce variance and improve statistical confidence. So now we know the process of how the MMV-based approach works. What are the benefits of using these MMV-corrected metrics in experimentation? The tech blog highlights several powerful outcomes. In some cases of experimentation, Lyft ran both user split and time split experiments for the same initiative to compare user-level and system-level effects. After applying MMV corrections, the user split results more closely aligned with the time split outcomes. This suggests that MMVs successfully corrected the interference bias. The team also performed a broad retrospective analysis across multiple experiments, comparing traditional and MMV-corrected metrics. They found out that in 10% of those cases, the launch decision would have changed had the MMV been used in the metrics calculation. These were evenly split between false positives and false negatives, suggesting that incorporating MMV-corrected metrics is very important for making the right decision. By embedding MMVs into their experimentation pipeline, Lyft now can test more precisely, adjust for marketplace-wide effects, and make better informed decisions at scale. Now that we've discussed both the business problem and the technical solution, let's wrap it up. In this episode, we explored how Lyft addresses interference bias using Marketplace Marginal Values. We saw how interference is a natural part of the marketplace dynamic, and how thoughtful modeling, combining the simulation and advanced algorithms, can uncover more reliable causal effects and help the team to make the best decision. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.